Okay, welcome to EGR 445. We have talked about spur gears. We looked at the design process for spur gears, and today we are going to start with helical gear. So, in today's lesson, what I'm going to do is I'm going to discuss the helical gear design, and then I will work out a problem. If you have understood the process for the spur gear, helical gear design process is pretty similar. Can someone help me with the overall spur gear design process? What is step number one in spur gear design? Correct. Correct. So first step is to see whether the pinion is weaker or the gear. We always design the weakest element. Then we find out the pitch line velocity and find out the value of WT. If the service factor is given to us, we would use the service factor to find out the actual load. Then we find out the velocity factor. Then we use the Lewis's equation to find the module. Then what do we do? Then we find the dynamic load, WD. WD is the static load plus the inertial load. And then we find out the static load, and then we find out the, the wear load. And then finally we check that the dynamic load is less than WS and WW. That is pretty much the exact same process we are going to follow for the helical gear. Yeah, I am coming to that. So first and foremost, let's understand what a helical gear is. So helical gear. In case of spur gear, if you see the gear in the top view, this is the top view of the gear. You would see teeth cut like this. This is how the spur gear would look like. Now, if you look at the helical gear, instead of the teeth being cut parallel to the center line, this is the center line of the gear, the teeth are cut at an angle. So for the helical gear, so teeth are cut at an angle. And this angle is called as the helix angle. This angle is called as the helix angle. And this helix angle is usually denoted by alpha. And what is the advantage of the helical gear? As you can notice that the helical gears, since they are cut at an angle, the effective face width of the helical gear is more than the spur gear. In other words, helical gear for the same size would be able to carry more load compared to the spur gears. And the reason for that is, observe the spur gear face width, the effective face width is this. But for helical gear, the effective face width is larger for the same footprint. Now, in the case of helical gear, there is a concept which is called as overlap, and I would just write it here. This is called as the overlap. Then there is something called as the no- the pitch or circular pitch, PC, and there is something called as the normal pitch, PN. So this is PN. And the relationship between the circular pitch and the normal pitch is given as Pn is equal to Pc cosine of alpha. And if you look at the equation, this equation is nothing but a trigonometric relationship. If you construct the triangle, that is the trigonometric relationship between sines and cosines, and that gives you the relationship between the normal pitch and the circular pitch. Other important thing that I want you to note is tangential load on the helical gear would be something like this. So this is the tangential load. But the component of the normal load would act perpendicular to the face width. So this is going to be F of N. This is going to be F of T. And let me draw a slightly bigger figure. So and I just want to show the loads on the helical gear. If this is my helical gear, if this is my helical gear, and then Wt is obviously the load that is causing the torque, Wt. Wn will be something like this, and you are gonna get Wa, and this is extremely important, and I want to show this as an important component. This is called as Wa. Please observe, in spur gears, Wa is not present. In the helical gears, because the teeth are cut at an angle, you have an axial load. So what happens is, if you have a helical gear would have an axial thrust always acting on that gear. It's a good thing and a bad thing. So for an example, when it's a good thing, imagine that this helical gear is somehow attached to a bearing that needs to be continuously preloaded. Then this axial load would be used or will be preloading the bearing. If this helical gear is attached to a clutch, and that clutch needs to have some sort of normal load for operation, then this helical gear, by the virtue of the helix angle, would be supplying that force to make sure that the clutch plate is in positive contact. Where it's a bad thing, it's a bad thing where you don't, you just imagine a case that if you want to use uh, uh, an inexpensive bearing, Not all the bearings are designed to take axial loads. So you would have to use maybe a taper roller bearing, or you may have to use a thrust bearing to compensate for this axial load. So this is a typical characteristics of the helical gear, that the helical gear would always give you an axial load. Now, helix angle alpha can vary anywhere between 20 degrees to 45 degrees. This is the variation of helix angle. And addendum, which is the distance from the pitch circle diameter to the tip of the tooth, is usually 0.8 times module. Dedendum is usually 1 times module, and then there are the tool depth is 1.8, and minimum clearance and thickness. So these are the standard proportions. Now, one important thing that I just want to mention here is, if you look at the Spur Gear design process, we find out the Lewis form factor. So we find Lewis form factor. This Lewis form factor Y is to compensate for the variation in the section modulus. Yes. So Lewis form factor is given by Y.
Every gear will have different addendum and dedendum, right? Like the table is shown.
What?
Different material will have different addendum.
No, different material gear proportions will be the same. Different materials will not have different addendum or dedendum. Geometry of the gear would be the same, but depending upon the different material, the torque transmission capacity of the gear would be different. So Lewis form factor, and that Lewis form factor equation, if you recollect, it was of the form, and I'm just gonna give you a Lewis form factor equation. Say y is equal to, just for the sake of discussion, say 1.154 minus 0.912 divided by number of teeth. This was the equation for Spur gear. This equation needs to be modified for the helical gear. For helical gear, instead of T, we use TE. TE are the equivalent number of teeth, and equivalent number of teeth is given as T divided by cosine alpha cube. So the only difference to start with, in the very first equation, when we find out the addendum, Lewis form factor equation needs to be modified. So as usual, same steps. Step 1 is find value of WT. WT is given as P divided by V multiplied by service factor. Next, check if the gear is weaker. Check if gear or pinion weaker. And how do we do that? To check if the gear is weaker or the pinion is weaker, we have to look at the product of sigma O multiplied by Y for gear, and we compare that with sigma O times Y for pinion. But one thing that I want you to notice, that the Y value that we will use here will come from equation 1. So Lewis's form factor, what we are going to use, should be found out for the helical gear. Then what we do is we have Wt, we equate that with sigma O multiplied by Y multiplied by the velocity factor Cv multiplied by B multiplied by pi multiplied by M multiplied by Y for the helical gear. And if you refer to the book, he refers this Y as Y prime, just to denote that this Y is different than the Y for the spur gear. And from this equation, assuming the ratio of B over M, we should be able to find out the value of M. One thing that please note, CV, the velocity factors for spur gears are different than the helical gears. So for an example, for helical gears, the velocity factor is 6 plus V when the velocity is greater than 5 meters but less than 10 meters. CV is 15 divided by 15 plus V when the velocity is greater than 10 meters but less than 20 meters. So CV values are different. Next step is we find out the dynamic load. So we have to find out the dynamic load, and please observe the equation for dynamic load is different for the spur gear. For helical gear, equation for dynamic load is Wt 21V BC cosine square alpha plus Wt divided by 21V plus square root of BC cosine square alpha plus Wt. Now this equation is different than the spur gear design. In the spur gear design, we did not have cosine alpha, and this alpha is nothing but the helix angle. The B is the face width, C, uh, all these parameters we used in the case of spur gears. So we will go back and refer to the same table from where we got the values of C.
Except just we will have the cosine like that angle.
Yeah.
But isn't it gonna like when we design the shaft, we consider like different kind of angle? Is this angle gonna have an effect on that? Tangential, normal.
Yeah. When we talk about shaft design, I will talk about what happens to the loading. Just bear with me for a second. Then next thing is we have to find out the static tooth load, WS. The static tooth load is sigma E B pi M y prime. And sigma E is the endurance strength of the material, B is the face width, M is the module, and Y prime is the Lewis's form factor for the helical gear. And as you know, the next step is to find out the value of WW, which is the wear load. This wear load equation will also have cosine alpha term. So WW will have dP, which is the diameter of the gear or the pinion. B is the width of the gear or pinion. Q value, uh, and Q value and K value, they are similar. So depending upon whether you have an external gearing or you have an internal gearing, the ratio factor would be different. So Q is the ratio factor, but K, the equation for K will be sigma E square sine P divided by 1.4, 1 divided by EP plus 1 divided by E.
Where do you get the EP and the AG values from?
From the table at the back of the book. EP and EG are the Young's modulus for pinion and gear, but PN is the normal pressure angle. And obviously, for gear design to be safe, WS has to be greater than WD.
So is WW.
WW is greater than WD. The last part of the problem, and this is slightly tricky for helical gear design, is the shaft design. And before we talk about shaft design, I just want to draw a three-dimensional pictorial view of the loads that are coming on the helical gear. Now, and let's start with a simple case of spur gear. So, this is, assume that this is a spur gear. So you have this spur gear. So on this spur gear, you have a tangential load WT. Everyone with me so far? WT is the tangential load. Because of the pressure angle, you are gonna have a normal load WN. Do you agree with me? And this angle is nothing but the pressure angle. So this angle is pressure angle. Now, since we have a normal load which is at an angle phi, whether we like it or not, we will have a component of normal load in the radial direction, which is WR. So this is the force diagram on the helical gear. Once again, WT is a tangential load that is causing the torque. Tangential load WT makes that gear rotate. But this tangential, because of the pressure angle, we get WN. And recollect, WN cosine of phi is equal to WT. So once we know WT, we can find out WN. And WR is equal to Wn sine of phi. And just to give you a quick overview, what happens because of Wt? Wt not only gives the torque, but when you are designing the shaft, and imagine the shaft is over here. When you are designing the shaft, Wt causes shaft to bend in the horizontal plane. On the other hand, if you look at Wr, Wr is going to cause the shaft to bend in the vertical plane. That's why you have to find out the bending moment in the horizontal plane, bending moment in the vertical plane, find out the total resulting bending moment, and then you have to use the equation to find out the total torque and then do the shaft design. Remember the process? So, Wt will give you a bending moment. Wt will give you a bending moment. Wr will give you a bending moment. These two bending moments are perpendicular to each other. So you have to find out the resulting bending moment. And then you have to find out Teq is equal to square root of m resultant plus t square. And then do the shaft design. This is the process that we used. This is for the spur gear. This is the spur gear. Now let's look at the helical gear design in little bit more detail. So you have a tooth, but instead of being face width and instead of the tool tip being parallel to the shaft, now it is at an angle. So I'm just showing the one tooth, but if you look at the helical gear, the second helical tooth, then it's again going to be like this. So let's start with Wt. Wt will be in this direction. Now, when you have Wt in this direction, recognize that you are going to have a component of Wt. I mean, you will have Wn here, and this angle is going to be alpha. So, however, recognize once again that this Wn is the projection of Wn bar onto the plane. So you are going to have another Wn over here. This is Wn bar. And this angle is the pressure angle. And the and this is going to be WR.
We talk about pressure angle in the homework question.
Yeah, pressure angle is for gears, you have pressure angle. So
for the quiz, we don't have pressure. We assume yes. 14 or 20, right?
Yeah. Okay. This force diagram, I just want to make sure that everybody understands the forces that we are having here. One thing that I want you to recognize that there is going to be a tangential, there going to be an axial load, which is Wn, component of Wn in this direction. So this is Wa. And what I'm going to do is, let me see if I can give you a three-dimensional pictorial view of the forces. What I'm going to do is, in the case of helical gears, you do not have a very simple uh, force structure. You are going to have a quite complex three-dimensional state of forces. So I will try to explain this once again. Okay, so imagine this is the axis of the gear. This is the axis. And you have one force which is Wt. So this is going to be Wt. This is going to be W. Actually, this is Wt. This is going to be Wn. This is going to be Wa. And since this Wn, there is a pressure angle here, you are going to have a component of Wn, and that component of Wn is going to be somewhere uh, like this. This is going to be Wn bar. And last but not least, Wn bar will have Wr. So these are the forces that are acting on the helical gear. I would explain once again. First and foremost, understand in helical gear, you have a complex state of forces because you have two angles. You have a helix angle and you have a pressure angle. So start with Wt. Wt is making angle pressure, making angle alpha with respect to Wn. So this angle is alpha. This is the helix angle. And as soon as you have the helix angle, we have the equation Wt is equal to Wn cosine of alpha, and Wa is equal to Wn sine of alpha. Are you with me this so far? So if I were to draw this triangle slightly bigger, this is what you would see. Wn Wt and Wa. But recognize Wn actually needs to be uh, along the pressure angle. So this angle, and this angle is tricky to show, but I want you to recognize this. This angle is pressure angle phi. So if you look at so this is the picture from top view. So if you look from top view, this is the top view of the force diagram. If you look at the front view, in the front view, you will see something like this. You would see Wn, Wn prime, and Wr, where this angle is the pressure angle, and this angle is the helix angle. Everybody with me so far? This is the front view. So if you were to see from here, this is what you will see. This is the top. If you were to view from top, this is what you would see. So now let's take a step back and then try to understand how these different forces are going to cause shaft to be bent in different orientation. First and foremost, you are going to have bending because of Wt in the horizontal plane. Do you agree with me? Wt is going to bend the shaft in the horizontal plane. Wa is actually not going to bend the shaft, but it is going to bend the gear. So Wa will give you an axial force that will be towards the bearing, and Wr is going to bend the shaft in the vertical direction, in the vertical plane. So everybody understood this?
WR is in the okay.
So Wr is vertical and Wt is going to be horizontal, but calculation of Wr and Wt, you have to be very careful. Wa is gonna give you an axial load. Now, depending upon how complex or how accurate you want your analysis to be, you can look at Wa as if it's giving you a couple or a moment at that location.
What do you mean by axial load? Is like going through the shaft?
Okay, let me draw the diagram for the gear. So this is the gear. Now you are gonna have a Wt, something like this. This is Wr, sorry. You'll have Wr. Wt is coming towards you. Wt is coming towards you. So I'm gonna show it like Wt. And Wa is going to be something like this. Now recognize what is this WA doing. If you think about the shaft, this WA multiplied by R, WA multiplied by R is actually causing a moment at this location. So when you are trying to draw the bending moment diagram in the vertical plane, you have to take into account the moment given by WA, and that moment because of WA would actually be a jump in the bending moment diagram. But sometimes if the gear dimensions or the pinion dimensions are small, you can ignore the moment given by WA. So everybody understood the process of the gear design. So this is the loading or the forces on helical gear. So what I'm gonna do is actually I will try to work out a problem. Okay, do you have the homework problem by any chance? Wow. Wow. It's due next week, right? Yeah. I just wondered. I mean, I gotta get it done this Tuesday. Okay, awesome. Oh, this problem is quite simple. Says you. Okay. But what I will do is, but what I would do is, I would go ahead and actually do the shaft design as well for this problem. So the homework problem number 1, design a helical cast steel gear. So it's a steel gear. Helix angle alpha is equal to 30 degrees, and it has to transmit P is equal to 35 kilowatts at speed of 2000 RPM. If the gear has 25 teeth, so T is equal to 25. Find the necessary module. So we have to find out the module M. Find out the pitch circle diameter PCD. Uh, and the face width B for 20-degree full depth gear. Involute T. Static stress for the steel may be given as sigma O. Static stress for the cast steel may be taken as 100 megapascal, which is 100 newtons per millimeter square. The face width B can be taken as 3 times the normal pitch Pn. So Pn is nothing but the normal pitch. And tooth form factor is given by the equation. So they give us the equation as well. 0.154 minus 0.912 divided by TE. and the velocity factor CV is equal to 6 plus V. So velocity factor is given to us. Uh, Lewis's form factor correction is given to us. Then, uh, and to be honest with you, he's just asking for M, PCD, B. He's not. It's not a complete design problem, so he's not asking us to check for the the wear load, and he's not asking to check us for the static load. But let's try to work out this problem completely. So first step, here they don't give us any type of service factor. So I'm gonna use CS, which is the service factor is equal to 1. When the service factor is equal to 1, then what I'm gonna do is I'm gonna find out the value of WT. WT is nothing but P divided by V multiplied by CS. Now the question is, how do we find out the value of V? Now value of V is dependent on actually uh, the pitch circle diameter. So we will keep V as, so V is equal to pi dn by 60, and I'll keep this as pi multiplied by d is the module multiplied by number of teeth multiplied by n divided by 60. So this equation is gonna look like pi multiplied by m multiplied by number of teeth they are given to us, which is 25, multiplied by n, which is 2000, divided by 60. So this will give me the value of V. So power is equal to 35 kilowatts divided by the value of V. Can someone tell me quickly what is the value of V? It will be in terms of M. 2680. 18 M. So 2618 M multiplied by, say, service factor 1 is going to give me the value of WT. Next step, step number 2, the equation for Lewis's form factor is given to us. So y prime is equal to 0.154 minus 0.912. Here we have to substitute equivalent number of teeth, and equivalent number of teeth is 25 divided by cosine 30 cube. So tell me the value of y prime, because the number of teeth are 25, but in Lewis's equation you have to use 25 divided by cosine 30 cube.
What is the difference between y and y prime?
Y is the Lewis's form factor for the spur gears. Y prime is the Lewis's form factor for helical gears. And the difference is when you are doing the spur gear, you just use the number of teeth. In the case of helical gear, we use equivalent number of teeth, which is TE. And TE is equal to T divided by cosine alpha cube, where alpha is the helix angle. Does it make sense? So tell me, what is the value of y prime? 0.130. So now next part is we have to use the equation Wt is equal to sigma O multiplied by y prime multiplied by uh, pi times m times b multiplied by cv. So in this particular problem, we even don't know what is the velocity factor. So for the velocity factor, we will use the equation that they have given us. Velocity factor CV is equal to 6 divided by 6 plus V, and equation for V we already know, 2618, which is 6 divided by 6 plus, the only one thing that I want you to be careful about is this velocity factor. Velocity has to be in meters. So I just want to be clear, and this is a mistake that students make. So this module is assumed to be in millimeters. Okay, so this velocity is actually in millimeters per second. But when we calculate the velocity factor, this has to be in meters per second. So this is 2.61 m, and that gives you the value of velocity factor.
I wonder why when we gone through like any problem that has English engineering systems, or do they not use the gear manufacturer?
We can solve in English system. You want to in HP, we can solve a problem. I already have the collections of problems. So the only difference is some of the equations, like for the wear load and those equations, they are different for English units. Okay. Now B is equal to 3 times normal pitch Pn, and normal pitch, as we know, I gave you the equation for normal pitch. Normal pitch is PC, which is the circular pitch multiplied by cosine alpha. So 3 multiplied by PC times cosine alpha, where PC is the circular pitch, and circular pitch is nothing but pi times module. So circular pitch is pi times the module multiplied by cosine alpha. Uh, so in this entire equation, the left hand side, Wt is 35 10 to the power 3 divided by 2618 m. And I just have to be careful here. This V should also be in meters per second. So I need to make this correction here. Just don't forget this decimal point. 35 10 to the power 3 divided by 2.61 m is equal to sigma O. Be careful with sigma O. Sigma O is 100 megapascal, which is 100 Newton per millimeter squares. So I have 100 multiplied by the value of Y is 0.130 multiplied by pi multiplied by m multiplied by B is 3 times pi m cosine of 30 multiplied by CV, which is 6 divided by 6 plus 2.61 m. This long expression has only one unknown. So this equation, there are two ways to solve this. If you have scientific calculators, then the calculator will actually solve this equation and give you the value of m. Yeah, it's going to be a cubic equation. So
when I solve it, like in the online calculator, I use the three results, like negative, positive, so just use the one that is most active. So like,
no, why do you need to use online calculator? With you should be able to use your regular calculator and get the answer. I think even your phone, you can. There is an app for scientific calculator. That okay.
I think you have to pay to buy.
I don't know. So this everybody understood the process. So once you find out the value of m, next step is to find out the pitch diameter. Pitch diameter, which is PCD, m times t, module multiplied by number of teeth. Now a word of caution, and please pay attention to this. This t is the, it's not TE. It is the actual number of teeth, not the equivalent number of teeth. What do I mean by equivalent number of teeth? Equivalent number of teeth is if I were to construct a spur gear that is similar to the helical gear that we have, how many number of teeth it would have. And why do we have to convert a helical gear into an equivalent spur gear? Because Lewis's equation is derived for spur gear. But our gear is a helical gear. So we will be considering T, not TE. TE will only be used when you are finding out the value of Y prime. Everybody understood this? Okay, PCD is equal to MT. Anyone got the value of M? Not yet? Okay. The face width, we already have the equation for face width, which is B, which is 3 times pi times M multiplied by cosine alpha. That gives you the face width. And the last part is necessary module. So we need to find out the module. Okay, any questions, concerns, ideas? No, but once we know value of module, we have to first solve this equation to module. Once we know the module, we can find out the pitch circle diameter, and then we can find out the width.
Why did you get B equals to 3 p.m.?
Can someone tell me why B is equal to 3 pi m cosine alpha? Why did I write B is equal to 3 times Pn? Because that is what is given in the problem.
All equations you get is put together.
So he's saying that the face width may be taken as 3 times the normal pitch. And what is normal pitch? Normal pitch is a circular pitch times cosine alpha. Okay, now we have a choice. I can go ahead and do uh, the wear loads and others sigma s for this, but for that I would just need the value of module. But if calculation of module is seeming okay, so I totally get it. Okay, now here is when I started, I did not have scientific calculators. So here is what we do. Engineers do the best, trial and error. But the issue is, where should you try? Right? Somewhere you have to try, but then the question is, where would you try? So here is the back of the envelope calculation. So let me simplify this equation a little bit. So 35 times 10 to the power 3 divided by 2.61. Okay, 2.61 is equal to this m. So I'm going to write this equation down. 100 multiplied by 0.130 pi m square multiplied by 3 pi m cosine 30 plus 6 divided by 6 plus 2.61 m. Can you tell me what is the number on the left hand side? 13.4 times 10 to the 3. No, I took the m on the other side. Yeah, here, 3 point in the last, my pencil work. Can you tell me the combined number 100 multiplied by 0.130 multiplied by pi multiplied by 3 pi? 2000.07 m cube plus 6 plus 2.6. Yes, times CV, right. Right, right. You're right.
Yeah, I multiplied that all out already. So the 6 is gone. So it's just the 2000.07.
Okay. Okay. Very good. Okay.
That's where I'm at. But when I plug that in, it got x either equals 0 or negative 2 points something.
It can't be negative.
I know. That's why I'm double checking. So I think it's just that calculus.
Okay. Uh, let me go a step further. Let me go a step further. Take this 2000.07 onto the left hand side and tell me the number. So 13.4 10 to the power 3 divided by 2000.7. How much is it? 6.9 is equal to 66 point. Okay.
I had an extra 0. Yeah, so it's 6 point. 6.7. Yeah.
Okay. So 6.7 is equal to m cube 6 plus 2.
Let's try that. That's
Right. Okay.
So 6 millimeters.
Finally.
What was the name of the website?
Similar. But it doesn't matter if you don't.
So 6 millimeters. So 6. Actually, this equation is simple enough. If you plug this in the calculator should be able to give you the answer.
It's new.
So quickly tell me, what is the pitch circle diameter? 25 times 6, 150 millimeter. And tell me the face width real quick.
So what did we get? X equals to 5.04.
But are you waiting for B?
M equals to 5.04. Yeah.
I have B if you want that. It's 48.97. Usually was 48.9, so 49.
Okay, so we got the pitch circle diameter, we got the the face width, we got the module. Now let's continue on. Let's take the same problem and try to find out the dynamic load. So WD, which is the dynamic load. Equation for dynamic load is WT plus 21V BC cosine square alpha plus WT cosine of alpha divided by 21V plus square root of BC cosine square alpha plus WT. Now, with so you should be able to tell me the value of V, because our V was in terms of module. So V was how much is V? 2.6 multiplied by module, right? 2.6.
2.61. So V was 15.66.
V is 15.66 meters per second. We know the value of B. The only thing that we don't know here is the value of C. So for value of C, we have to go back to the table and let's look at, it's a cast steel material. So it's a steel. Uh, yeah, yeah. So basically 28.5. So from this is the same table for the deformation factor for the spur gear. And again, depending upon the error action, you can choose. I would use error action, say assuming E 0.01, value of C is equal to 110. This is table 28.5. So just error action E is equal to 0.01 millimeter. So WD can someone tell me value of WT? WT was in terms of module. Uh-huh. No, it's steel. Steel.
Isn't that for 14? Yeah, that's for 14, right? So,
Yeah, 119.
see,
Or actually, it's 114 to be.
almost 4.
Yes, saying stuff.
Right?
Yeah.
I just want to make sure I read it right, because I had to pick it in my quiz, and I was like, oh, wait, I don't get this right. Yeah.
Yeah. So WD. Tell me. I mean W. So tell me what is the value of WT?
That's what I want to do. Because remember, it's 13. That makes it.
So this is the equation. WT 3510 to the power 3 divided by 2.61 multiplied by m in millimeter. So what do you get?
So that WT is 2000.
2000. So 2.2 kilonewton. Twenty-one multiplied by 15.66 multiplied by the value of the face width, which is 49, 114 multiplied by cosine square alpha is 30 degrees, 2200 cosine 30 divided by 21, 15.66 plus square root of b 114 cosine square 30 plus 22. This will give you value of WD. Next step is to find out WS. For WS, we have to find out sigma E multiplied by Y prime multiplied by B multiplied by pi m.
So the WD,
Yeah,
WT
plus
will be in
newtons.
Newton meters, right?
WD is just newtons. It's a force. So this will be in newtons. This has to be in meters per second. This has to be in millimeters. This C is in Newton per millimeter. This has to be in newtons. This has to be in millimeters. This is Newton per millimeter. Newton. This is meters per second. And the reason these the units are inconsistent, so to speak, because this comes from the dimensional analysis. So for sigma E, I have to actually go back to the Spur Gear table, and it's a cast steel. So I'm gonna say for BHN of 240, sigma E is equal to 420 Newton per millimeter square for BHN. So Brinell hardness number 240 from table 28.8. Sigma E is 420. Y prime. Can someone tell me what is the value of Y prime? Actually, you told me earlier, right? 0.130. 0.130. B is 49. Pi. M is 6. So once we know WS, the last part is find out the value of WW. So for WW, equation is dP B Q K divided by cosine square alpha. Q is the ratio factor. Unfortunately, this is just one gear. We don't have, so I'm going to assume a ratio factor of 1. Say assume velocity ratio is equal to 1. So Q times VR divided by VR plus 1. So basically Q is becomes 1. Then we have to find out the value of K. Value of K. The equation for K is sigma ES square sine phi n multiplied by 1 EP plus 1 EG. So for the sake of discussion, I'm going to assume this gear is paired with the same gear. So this gear is paired with some same gear. So number of teeth is equal to same, material is same. So sigma ES we get from the table. Yeah. Unit strength is, I'm going to sigma ES is 400 square sine, the pressure angle is 20 degrees divided by 1.4 multiplied by, it's the steel, so 200 10 to the power 3. So this I'm going to be assuming this to be steel, mating with steel. That will get me the value of K. Once I know value of K, WW can be found out as dP multiplied by B multiplied by Q multiplied by K divided by cosine square alpha. dP is 150, B is 49, Q is 1 divided by cosine square 30. What is the value of K? What? How much is the value of K?
Yeah, we got WD. Just so you know. Yeah. Better than me. I know this.
Okay, so tell me, what is the value of WS? What is the value of WD? 3000, 6652 newtons. WS, and WW, K, value of K,
What question was this?
We're just adding on.
no, this is, yeah, I'm not solving any different problem. This is the same homework problem, but I'm continuing it to find WS, WW, and I will do shaft design so that you will have a complete gear design. I think in the quiz, I have asked you to do a helical gear, right?
Quiz 2. I'm sure.
Okay, good. So you have a helical gear. So once this problem is done, you can start with the quiz problem 1. Because I already solved homework problem for you. Homework 2, problem 1. Oh, I just went to the table, closed my eye.
You assume that one? It's steel?
Yeah, it's steel. So just look at the same table. Yeah. Yeah. So the other one is okay. Hold on. No, surface. Just a second. I will tell you where I got this number from. You are asking me about FES, right? Or are you asking me about sigma E? FES I got from 28.9. I looked at Brinell hardness number of 240. About between 150 and 200. So yeah. If you really want to be specific, there is a formula. Sigma ES is equal to 2.8 multiplied by BHN minus 70. If you really want to be very specific.
Oh,
Just be aware that everything what you say is being recorded. How much is it? 38,000.
3,800.
Are you sure? Is this a real number you got? Is that? Okay.
Well, but you have the 150 times 49 times 1.
Okay. So the equation is dP, which is the diameter of the gear, B, Q, and K. Now in K is 0.29, 400 square. So at this point, assuming these calculations are correct, as you can see that WD is 6652. So WD is 6652, but WW is 3822. So what it means is this gear will not be safe since WD is greater than WW, the gear is not safe. So the easiest thing to do is increase the value of B. So increase the value of B. So thus so we will say thus we increase value of B. Now so value of by twice we are going. Okay. So assume B is equal to 100 millimeter, and but here is something that you should be careful about. This B value also appears in the dynamic load equation. So which means there is one more iteration that is needed just for checking. That's a very thick gear. The other choice is you can go for a different material, but I have seen gears like that. So, so unfortunately, that is what it is in this particular case. So increase the value of B, but check WD, because your WD will change since the value of B is changing. Everybody understood this? Okay. And assuming you won't go into the infinite loop because WD increases. Yes. No questions? You understood everything? Right? Copy this. This is like you are doing your homework. Okay. The last part is the shaft design. So WT, we know already the value of WT, which is 2200. Can I just calculate the values of WN, WR, WA, or do you want me to explain the force diagram again? Yeah. So WN is equal to 2200 divided by cosine of 30. WR, I mean WA is equal to WN sine 30. WN prime is equal to WN divided by cosine of phi, and WR WR is equal to WN sine of phi.
Isn't there two shafts for this problem?
There's just one shaft.
No,
One
two shafts, right? Like there is like, the last page you draw.
just a second. Phi n is equal to so tell me the values. Well, I just want you to be aware of this equation. I actually made a mistake here. This actually is phi n. This actually is phi n, not phi. This is phi n. And phi n, you have to find out with this relationship tan phi n is equal to tan phi times cosine alpha. So just take a note. I just use phi n is equal to phi, but that's not the case. In this particular equation, you need to substitute the value of phi n, and phi n is tan phi multiplied by cosine alpha. So it's going to be phi is equal to tan inverse tan 20 times cosine 30. Can you just quickly tell me this value? How much is it? 17. 17. So please make a correction here. This is not 20. This is 17.5. I don't think that answer will change this number k significantly, but still I just want you to have the correct. Okay, to answer your question, Ghazi, we are designing the shaft for just one gear. So this is the gear that we have. So we are just designing one shaft. Okay.
What's the difference between W W W dash N and WN?
Okay. Remember the three-dimensional force diagram that I have drawn? Wn is the component of Wn dash, Wn prime in the horizontal plane.
That is the WN dash.
Yeah, on the left hand side, you see Wn.
Oh.
So, yeah, can you please tell me these values? Wn,
Two 2540.34 WN.
2540 Newton. Wa,
1270.17. What is my cosine phi?
cosine phi is 30 degrees.
Is 30 degrees?
30 degrees.
2932.94. I think 2933.
Wn is how much?
2933.
2933. And Wr?
1466.5.
So let's look at the loadings. So I'm gonna draw front view and top view of the gear train. I mean the gear.
And problem 1 from the quiz is similar to this one.
I don't remember. So here, this is Wt. This is Wr. And one thing is about Wa. you can assume WA depending upon uh, how that gear is configured. For example, if you have the gear pair on top of each other, then you can assume WA to be like this. WA. So everybody understood the loading diagram that I have shown here? WR is 1466. WA is 1270. WT is 2200. Now I'm assuming two bearings, one on either side of the gear. Since we assumed the face width to be 100, I am saying the center distance between the bearings to be 200. And this is my assumption. Since the face width is 200, I am assuming the center distance between the bearings to be 200.
Last time you used same on both sides. Why?
Last time I used.
Last time, like last. Remember when you were doing the quiz problem, the distance was like 70 and it was 70 on each side.
Because there were two gears on each side.
Okay. So in this particular problem, the reason for that, the loadings are small compared to the previous problem. So that's why I'm assuming. But nobody has prevented you from going 250. As long as it is not is equal to 100, it can't be 100. Center distance between the bearings cannot be 100. It has to be greater than 100. So, but it has to have some clearance. So that's why I'm assuming 200.
It could be 110 as well. But is that a problem?
Okay. Just to give you a physical understanding of what is the implication of that. This is 100. Agreed? 110 means the bearing center line would be somewhere here. That's very close, which means your overall bearing width cannot be more than 10 millimeters. You see what I'm saying?
Right.
That's why means there is a, it's possible, but I don't know if you can find a bearing with the overall width of 10 millimeters when your gear is 100 millimeter wide. That's why I just use this. Does it make sense?
Yeah.
Okay.
100 millimeters still like this.
100 millimeters. 100 millimeters is 10 centimeters.
Oh,
Okay. All right. So this is the loading force diagrams. Now, what we need to do is find the reactions. After finding the reactions, we have to find out the bending moment. Does it make sense?
bending moment. So one more question I had from the quiz. Do you want us to draw all the shafts and then do the bending moments, or do you need bending moments for each different shaft? Shaft design.
To find the diameter of the shaft,
Yeah.
you have to find out the bending moment first. Then you will find out the total bending moment. Then you will find out the TEQ, and then you will decide the shaft diameter, just like what we are doing here. So now tell me the bending moments here. So bending moment here is, I'm gonna call this is the front view. So this is the front view. So I'm gonna call this M1, which is WR times 200 divided by 4. Then there is M2, which is 1270 multiplied by this distance, which is 75. And here there is M3, which is WT multiplied by 200 divided by 4. Now at this point, uh, I just want to have a little discussion on the planes in which these bending moments would act. If you look at WR, WR is going to bend this shaft like this. WR bend this shaft like this. This is the front view. If you look at WT, WT is going to bend the shaft like this. This is the top view. Now my question to you is, and I want you to answer this question very carefully. What happens with WA? How would WA bend?
This which is counterclockwise.
So in other words, the question I want to ask you is, how should I find out the resultant bending moments? Okay, so check this out. And this is, everybody understood where the confusion is. At this point, I got three bending moments, M1, M2, and M3. And this is particularly for the helical gear. Because in helical gear, you have the tangential load. In the helical gear, you have an axial load, and you have a radial load. Now, WA, if I were to find the reactions, do you agree with me? The WA will be supported by the reactions like this. Agreed? They would be, because WA is in the axial direction. So the reactions has to be axial. So the moment given by WA will actually get added. So this will be M bar, which is M1 plus M2. And the total moment, MEQ, or M total or M resultant, is going to be square root of M bar square plus M3 square. Does it make sense? Because this axial load is bending the shaft, but this axial load, if you think about it for a second, the shaft is gonna get bent something like this. It's going to bend the shaft in the same direction as the the WR is bending. So you get MR. Next step is we know the value of torque. So we find out the TEQ. TEQ is square root of T square plus MR square. And assuming steel shaft, tau is equal to 45 newtons per millimeter square. Tau is equal to TEQ divided by J multiplied by R. 45 TEQ needs to be in Newton this should be Newton millimeter. J is pi by 32 T to the power 4 times T by 2. So can you please tell me values quickly? What is the value of MR? So we'll start from here.
So M bar, yeah. So M bar is
Yeah.
168.5 kilonewton.
Okay. M3. Kilonewton millimeter or kilonewton meter? Then you will get MR. Yeah, but this is in Newton millimeter though. This is in Newton. This is in millimeter. This is in Newton. This is in millimeter. This is in Newton. This is in millimeter.
Because it has to stay in.
So once you do this, substitute the value, and as you know, the value of torque, we already know. Torque is Wt multiplied by the radius. Wt is 2200, radius is 75.
You get a diameter of
5 millimeter?
Yeah.
Yeah, that's too small. But so most likely there is an error between kilonewton meter and kilonewton millimeter. That's type of stuff. Because your M value is quite large here, 110 kilonewton meter. So tell me what is the value of MR? So 201. So 201 is kilonewton meter. Is that right? Okay, assuming you follow the process, you find the value of MR, then get the value of torque from here, substitute this value of torque in this equation here, MR value over here, you find the value of TEQ. This TEQ needs to be substituted here, and the only unknown in this equation is D. So find D. And that is how the shaft is designed. And that's it. This is where we stop for the helical gear design.